Okay, we're all set? Okay, thank you. Thanks everyone for coming today. And this session will be a great opportunity for EASP to look at its role in supporting all the folks and the work that keeps Earth data secure, available, and durable. And I want to thank all the invited speakers for coming out to Tacoma for this meeting and for their expertise in the special skills required to keep Earth and other information and infrastructure going. And I want to thank Mark for suggesting this session. And last, I want to thank the Alfred P. Sloan Foundation for supporting the travel for this breakout. Now, the maintainers are a new online collaborative, and they build collective intelligence and coordinated learning opportunities for anyone who works to keep things going rather than inventing new stuff, which they totally could do. But then the online data would die horribly, and all of us would lose our information resources, and then our jobs, and then the planet would be at risk. Now, the maintainers bring a very social, caring mindset to their jobs, and they demand that this practice be acknowledged. And what they're up against, and what we sort of all face, is a market logic, science needs to be run like a business style mindset. And there are lots of ways that the rational, logical, hyper-competitive, winner-take-all, zero-sum, prisoner's dilemma, nice guys finish last, single bottom line, productivity up ratchet mindset is just wrong for sustaining Earth data and information. Of course, that kind of mindset's wrong for the Academy in general, and it brings the worst of 20th century corporate management practices into government. It describes a race to the bottom of some neoliberal fantasy future where we really don't want to go. So what do you say we turn around and go the maintainers' way? Today's talks will look at the diligent work of those who do their best to keep things running most of the time. And they do this with generosity, care, and kindness. Now, kindness is a normative human practice in a wide range of social frames: parenting, friendship, governance, teaching, caregiving, civil interactions. And Jonathan Zittrain reminds us that the internet was built on kindness and generosity. In Aristotle's teachings, kindness is a component of phronesis, an entire type of wisdom that we've devalued for the past 400 years. But that's another talk. And in Latin, the word for kindness is humanitas. Like rationality, kindness is a form of practice, not an emotion. You can no more feel kind than you can feel rational. But unlike rationality, kindness necessarily involves others, their perspectives and needs. Kindness is a normative practice. It can be judged by others for its qualities. Is it genuine? Is it motivated by a need to be perceived as kind? Is it effective in performing its intention? And what is its intention? In the academy, where intellectual judgments run wide and deep, kindness opens up another opportunity to be judged. But so does being unkind, or so it should. For decades, the lack of kindness in our institutions and workplaces has gone unremarked upon, and it's time to remark these. In nearly every human social endeavor, kindness matters, even in highly competitive sporting events where sportsmanship is highly valued and is actually a form of kindness. But why should kindness be absent from research labs and management in the academy and government service? Feminist sociologists remind us that the banishment of kindness is a necessary part of the academic workplace. It's another toxic impact of hypermasculinity in the academy. One consequence is that this allows academics to defer judgments about being kind, which means it's okay to be unkind. Nobody expects something else, but we really should. And why does ESIP and maintainers need kindness? Well, one feature of kindness is that it enables one half of the double meaning of the term care. To really care, and it ennobles the other half, to really care about someone or something, you need to tap into genuine kindness. To care for someone or something can be merely a job, but this job is also reduced without the intention of kindness. And that's why maintainers call on kindness to care for each other and for the resources we all share. Maintainers insist that it's time to put care back in your career. We can also reflect on the qualities of kindness in our own lives. And as high-functioning adults, perhaps we should do this more often. Real kindness begins with a clear intention, and this requires a measure of self-judgment and reflection. Without reflection, you cannot actually be kind. Even if others might interpret what you're doing as kind, you can fake it, but you can't make it. So how do you actually judge your own intentions, particularly in relationships with other people and things? And that's where culture shows up. Culture provides a layer of meaning for intention that can turn a social activity into a caring, helpful conversation, the kinds of conversations we have out in the hallway here. Our intentions are formed by culture, and those mindsets I mentioned above also emerge from culture. And as a caveat, culture also provides the layer of meaning for intentions on fear and hatred, but that's another talk, and that's in the newspaper anyway. The social always contains this layer of culture. There is no social without it. The best organizations cultivate a conscious culture layer by fostering internal communities that share and honor collectively considered values. Here, we follow the ESIP way. It's not a law or a code. It's how we respect and learn from each other. It's why we get things done and have fun at the same time. We really are way too nice, but that's how we like it. ESIP and the maintainers represent two faces of the Earth Data Commons. ESIPers add value and pull value from these information resources. Maintainers shepherd the endeavor over time. We share a common need to preserve and maintain Earth knowledge. We're all commoners, commoning for the future of the planet. And today, starting with this breakout session, we hope to find new ways to work in concert toward this shared goal. Thank you. And now Mark will. Here you go, Mark.
Thanks, Bruce. So I just wanted to introduce the maintainers. I think Bruce did a really good job of capturing the spirit of the group. It started with a paper essay written in 2016 by Lee Vinsel and Andrew Russell, who are science historians, science and technology studies scholars, called Hail the Maintainers. It's in an online magazine called Aeon. I encourage you to look it up. And it was basically calling into question this sort of cult of innovation, this fetishization of innovation, and challenging the move fast and break things attitude, and recognizing that we need to have more emphasis on maintenance, as Bruce was describing. And then they had two conferences, the maintainers, and talking about maintenance of all things. And then it kind of lost momentum, but then sometime last year, a group sort of spun up just sort of ad hoc thinking about the information maintainers, which I think we all are. And so there's a subgroup of the maintainers called the information maintainers. And as it says here, the purpose is to support the maintenance of information in those who manage, maintain, and preserve information systems. And you can get to them at that website there. And also to highlight that the maintainers writ large will be having a conference in October in DC, and that's the second link if you're interested in attending that. And we'll be having an ESIP related session at the maintainers as well. So this ad hoc group of information maintainers met virtually for a number of months, and we ultimately decided to write this paper, Information Maintenance as a Practice of Care. An invitation to reflect and share. And this concept of care as a practice of care really comes from feminist studies, some degrees, critical social theory, and so forth. And it's been a really interesting group for me to work with, coming sort of from the physical sciences and working with Marxists and feminists and really people really questioning the way we do things. And we cast this paper as a potluck, that we brought dishes to the table. The 40 or so people who participated in writing this paper brought, our perspectives, our views on things. But by casting it as a potluck, we're inviting you to come and bring your dishes, your perspectives to the table as well. And the paper is really just sort of overview of what we mean by maintenance, what we mean by information, what we mean by care, and trying to develop this sort of caring practice and define what we care about, everything from your local care, your home, your garden, your family, to your communities, to and beyond, and then really discussing what knowledge organization systems are and how they require care, and emphasizing that maintenance does not mean preserving the status quo. It means ensuring that we can continue to develop and go forward. And it also means that we should not be maintaining pejorative negative systems as well. And we have to recognize that maintaining information, even defining what information is relevant, is an act of power. And the powers that be that define what information is important actually play a critical role in society. So we have an obligation to not maintain the bad while and facilitating the appropriate powers. And then how do we demonstrate this? Through our communities, through our friends, and also through maintaining yourself, maintaining your own health and well-being. And then the paper is sort of peppered with examples, everything from interesting project that's trying to identify repositories at risk, either because of climate change or funding constraints or what have you, to the Black Lives Matter movement, there's an indigenous data sovereignty group that is coming up with something they call the CARE principles that accompany the FAIR principles. So CARE is collective benefit, authority to control, responsibility, and ethics. And so just really trying to open up this perspective on how these things work. So I encourage you to check out this paper. As I say, it's an invitation, and you're welcome to join the information maintainers. We're just having monthly telecons right now. Of course, this conference is coming up in October. And I think our primary goals in the short term is really sort of advocacy, just sort of raising the profile of information maintainers and the value that they provide. And because they're often hidden, they're often marginalized. And so just sort of raising that profile. And that's, I think, a vision of the maintainers writ large. So that's just a little bit of background on where the maintainers come from. So we'll turn now to our speakers, who will be talking specifically about maintenance in the earth sciences and why that matters, and the systems behind that. And so we have 4 speakers providing different perspectives. And our first speaker will be Emily Jane, I should have asked how to pronounce your name, Silak-Glassman, talking about the importance of maintaining Earth observational data for long-term climate record reconstruction. So Emily, please. Oh, there it is, good. I'll let you take this down. I don't know how to drive PowerPoint either.
Let's see. Great. Well, thank you, everyone, and thank you so much to the maintainers for inviting me here today. As Mark mentioned, I'd like to talk about the importance of maintaining Earth observation data for long-term climate reconstruction. And the framing that I'd like to use comes from the, comes from the Common Framework for Earth Observation Data, which talks about data management guidelines in 3 broad categories: discoverability, or whether a data user knows that the data exists and knows where to find it; accessibility, the ability for a user to retrieve that data; and the usability, or the ability for a person to apply that data to their application. So I'd like to talk and start by talking a little bit about the timeline for data provision. And I think we often focus on this very early part of the timeline. How fast can we get data out to users? So within 3 hours of data collection, let's see if we can do this. Let's see. Within 3 hours of data collection, the first near real-time satellite data products become available. And within 5 hours, there's some near real-time satellite imagery that becomes available. And this is really intended for disaster management purposes. Um, Within a day to a week, you start to have standard satellite data products becoming available. And finally, within 1 to 2 months, you have quality controlled local climatology products become available. And of course, after that time frame, there are things that are available quarterly, biannually, et cetera. And there's a lot of focus on this early stage of data provision. But the question that I'd like to ask is, what should we do if we need to use data or would like people to be able to use our data decades or even more than a century after the data is collected? So the example that I'd like to use is looking at climatological data, where you often want to have as long of a record as possible, which means using observations from as long ago as possible. Um, and that's really in order to identify trends. And here I'm showing a few trends. These were from the first volume of the most recent National Climate Assessment. So the way I'd like to do this is to take two examples in which people have used data from decades or even centuries prior, look at the kind of data management considerations in the common framework, and then from there see if we can extrapolate out some principles for long-term data use. So the first application I'd like to talk about was a recent paper in 2012 by researchers at Scripps, where they looked at, they compared data from the Argo program, which is buoy data. They used data from 2004 to 2010, and they were looking to compare ocean temperature data with data from the HMS Challenger, which was a sea voyage from the 1870s. And in fact, they were able to compare these two very different temperature records to find that the ocean surface temperature had warmed by 0.59 degrees Celsius. So for those of you who aren't familiar with it, the HMS Challenger was a first of its kind. It was the first purely scientific sea voyage that took place, sponsored by the UK, and it collected data for about 3.5 years all over the globe, all sorts of data, oceanographic data, botanical data, zoological data. I'm showing a painting of the Challenger on the left and the natural history workroom aboard the boat on the right. And so this is actually the voyage that the Space Shuttle Challenger was named after. So it was a very, is even today a very well-known voyage. One of the things that really helped with the use of the data of the Challenger is all of this, I'm going to say like metadata in quotes or ancillary data. There was there were many reports that were published after the Challenger voyage in the kind of decade after it finished. And it included instrument configurations, electrical diagrams, calibration information, pages and pages of really detailed content that enabled modern day researchers to use that data with modern measurements. And actually, there's an even more recent paper just this year, I believe, in Science, looking at deep sea ocean temperatures from Challenger. So a few takeaways in terms of data management, I would say in terms of discoverability, this mission is really well known, and because of the scope, the nature of it being first in its kind, discoverability is less of an issue. Accessibility was an issue, but was greatly improved by report digitization in the early 2000s. The paper copies had been held by a number of libraries, and they were digitized by actually a number of different groups. And I would say in terms of usability, it's these thorough descriptions of the instruments, the configurations, the methods that really allowed the data to be applied. Far more extensive than any, I would say, modern methods section in a research journal paper. So the other example I'd like to talk about was the first major American reanalysis project from the National Center for Environmental Prediction and the National Center for Atmospheric Research. So this was in the early 90s. The goal was to create a single unified atmospheric analysis record from 1948 to 1996. And this is challenging because when you're stitching observations from really different time periods, you can get jumps, and it's hard to know if those are coincidental with the fact that the record changed or an artifact of introducing new observations. So on the left, I'm actually showing the impact of an upgrade in the global data assimilation system. You can see the impact of the model changes as plotted against the actual output for this one parameter. And what made this reanalysis one project so challenging is not only does this span the time period of pre and post satellite data, but it's pre and post airborne weather data, and also the expansion of weather measurements from really being just over North America to being global. So the four major steps of the reanalysis were preparing the data, gathering the data from all the sources, pre-processing into a unified format, data assimilation, where you're essentially using the numerical weather prediction models not to forecast but to data gap fill, and then producing the many different outputs that you would want to that different communities might want to use. So I would say here, discoverability was not a major issue since the majority of the data came from well-known sources. Accessibility, for the American team doing this to get their hands on all the data, they really had to collaborate with researchers from other countries. They collaborated with the Japanese and European meteorological institutes, and that was necessary to get data that would otherwise not been obtained. Usability, it sounds like from reading the papers, was probably the biggest issue, where you had data sets where there are different issues per data set. There are location issues, date issues, and essentially the researchers had to develop a whole quality control pre-processing system in order to automate some of this, because it would have been far too labor intensive to correct otherwise. So in terms of what can we learn from these two different examples, I would say in terms of discoverability for uses that we can't imagine by people that haven't been born yet, it's helpful to archive the data in multiple major easily identified locations, national archives, major universities, in hopes that those librarians will help point people to the right resources. For accessibility, I think it's inevitable that data formats are going to change. So storing data in two different types of formats at a minimum, I think, is useful. A non-proprietary, open source, well-described format, as well as whatever the prevailing format of the day is. So for example, for a document meant for like word processing, you might want to store it in both a .rtf and .txt and a .docx. But periodic technology refreshes are going to be necessary in order to keep that data up to date and enhance the likelihood that someone's going to be able to use it. And I think this is really where maintenance comes in for data mostly. And then for usability, I think just like in terms of data formats changing over time, calibration abilities are going to change over time, new technologies are going to come in line, and it's difficult to know exactly how and why someone's going to use your data very far down the road. So unlike in, for example, disaster management applications, where the goal is to provide a very processed, easy to use format for a kind of known application, I think in this, yes, it's great to provide the calibrated process data, but also the raw data along with really detailed information about instruments, data collection practices, and any other kind of transformations that are often performed or should be performed, because that'll help researchers down the road make an informed decision. So with that, I'd like to thank you all for listening, and thanks again to the maintainers for inviting me, and I'd be happy to take any questions. Yeah.
Is it going?
Hi. So you said, oh, hi. My name is Anna Mylan. I work at NOAA at the National Centers for Environmental Information. So we archive climatological data, though I can't say it. You said archive data in multiple major, easily identified locations.
Mm-hmm.
And one of the challenges, one of the things that we want one authoritative archive and backup copies there, but we feel like maybe people get confused when there's two authoritative copies of the same thing out there, and which one's more? So can you just talk a little bit more about that?
Yeah, I mean, I think that, I think that type of thing makes me think about data.gov, where you have maybe the data is stored at one authoritative location, but there are multiple places pointing to that data. I think that that's probably a, in my mind, that seems to be a good practice, even with all the caveats of what data.gov has done well and poorly. But I see your point, is especially when we're talking about really huge volumes of data where it may not be realistic for you know petabytes of data to be stored at multiple different locations, to at least have records in multiple places that people might go to point back to the authoritative source. I think that would be my response. Yeah.
Nope. I have sort of a related
Sure.
thing. I think that there was a program that started many decades ago where the government would seed every government document out to certain libraries. And these are all over the different states. I think each state has one at least. And something like that for digital information sounds like a great idea.
Yeah.
Too. Even though they don't have to be active, they can
Right.
be dark archives, but just to have it around and just in case.
Yeah, that's certainly interesting. I'm not aware of that program, but I would be really interested to learn more about it. 'Cause I do think there's this tension between not wanting to duplicate too much labor or resources or effort, as well as having some amount of redundancy, and increase of access. And I think it's difficult to figure out exactly where that balance lies, especially as digital records get so much bigger. But it's a interesting concept. Yeah.
This is Mark again. Just following up on that, I'm sure most of you are familiar with the concept of locks. Lots of copies keep stuff safe. That's something really embedded in the library community. But then also there's this new initiative that I've been really intrigued by. I'm not involved with it, but it's called the Data Curation Network. And I'm stealing Daniella's thunder. So I'll just say briefly, maybe say more, but it's basically a coalition of university libraries that all have institutional repositories that are managing their data, but you can't have curation expertise in all disciplines. And so they have a mechanism for, basically putting out a call and sharing the curation responsibilities across these different. It's just a pilot project right now, funded by Sloan, but I think in about a year's time, they're going to be looking into extending the membership and so forth. And I think it's a really interesting concept. It's worth thinking about. Yeah.
Huh. Thanks.
Any other questions? Okay, well then we'll go to our next speaker, who will actually. Yep. Yay, Emily. Daniella Loewenberg actually comes from a library, the California Digital Library. And she will be talking about maintaining and growing research data publishing at the California Digital Library and Dryad. Oh, okay, I'll let you drive.
Oh, oops. Cool. Hi, I'm Daniella, and I was just reacting to that because I should probably say why I'm even talking about Dryad. So I'm a product manager at California Digital Library, which is a part of the University of California. And we have partnered with Dryad. And so I'm the product manager for Dryad. And the rest of the Dryad team is at the Data Curation Network meeting right now. So that's why it's funny. But Dryad is a partner in that project. So I want to tell a story today about maintaining for the UC researchers, a lot of them that are in earth sciences and that had been supporting Dryad, and how we could better support them at UC and how that has changed the path forward for Dryad. So thinking about the UC researchers, it's one of the largest institutions in the world for research, and a lot of the earth science is coming out of there as well. We have about 50,000 article publications a year. And when we had a data repository called DASH, we got less than 100 data publications a year. It just doesn't make sense. So we were looking at what were the hurdles. Why weren't we capturing the research outputs from our researchers at UC? One of them is that researchers don't think about their institutional repositories. They don't know about it. They haven't been told to go there. Publishers and funders don't name them when to go. I know because I worked at PLOS and told all researchers to go to all the general repositories, so shame on me. The next is that, of course, there's this recharge. So it's an institutional repository. We have 10 campuses, and they all had to deal with covering the cost of preservation, and that can be a huge burden. So why would administrators at UC push their researchers to go somewhere that they're going to then have to go back and pay for the terabytes of data? We have curators at the University of California, but they're not plugged into the process. So there's things like Dryad and others that the researchers are going, and especially the domain repositories that do massive amounts of curation. And we just weren't doing any. It was just really put your data here. And there was just no connection to a larger ecosystem. So thinking about the domain repositories in earth sciences and then the data that was going in DASH, there was no connection. And a lot of it probably should have gone to the domain of those 100 that we got in a year, and yet we were capturing it. So thinking about how could we maintain and promote this ecosystem for the UCs in a way that actually maintains the places that researchers are going. So we looked outwards and we found Dryad, and found is a crazy word for it because we knew about it. Does everyone here know Dryad? Again, nods. A few no's. Great. So Dryad is a general data repository. They started 10 years ago within the ecology community. A bunch of researchers at Duke and UNC got together with support from the NSF to think about how could we capture data that doesn't have a domain home. And so they started Dryad, and since then have had 28,000 deposits. So it gets massive amounts of data. And the reason that this happens is because so many journals are integrated and related to Dryad. So many journals are pointing people there and are integrated into that process, especially the society journals. We also have people like NSF that are pointing researchers to go there when they don't have a domain home. So it's captured about 90,000 researchers in the last 10 years. So it's obviously something that needs to be maintained and something that seriously we as a community need to be considering. One thing that's different about Dryad, I know that this is my first time at ESIP, but not my first time in the data community, to know that the general repositories, sometimes there's a weirdness with the domains and where the data should go. But the difference with Dryad that we have to be thinking about is A, it's researcher owned and led, and B, everything that goes into Dryad is curated. So unlike all of the general repositories, what actually goes in has a full, fair curation process through it. And so thinking about how could we as a community support that, we decided to go into a partnership with them at UC. And so for us, maintaining means meeting the researchers where they are and then maintaining and promoting those systems. And so one thing, while we know that Dryad has massive adoption and doesn't have a problem with researchers not knowing about it, we know that they had, to be honest, a really lame platform. Their platform couldn't iterate, they couldn't build new features, they couldn't keep up with the community, thinking about all the work that the last 2 days ago, all the sessions on fair metadata, just don't have that capability to put that stuff in. But what we at CDL had was an awesome platform with a development team and resources. So we were thinking, let's maintain that. So we're launching a new Dryad. And this is a screenshot of the new Dryad. And we're launching it very soon, but I'm never going to tell you a date until it goes live. And then you guys will be really excited, but it's going to happen this summer. So what we've had to do is think about what researchers need, what was valued in Dryad before, what did researchers really like about it, keep that, but then think about what features do we really need in the future? What are the big things that we need to put into this? And so if people were in the talk 2 days ago, I mentioned the ROAR project, Make Data Count, all these initiatives that we've had to put features into the system to support. So the platform includes a lot of maintenance. We had to put in a lot of things that would actually keep Dryad a sustainable functioning platform that met the researchers. So a bunch of the big differences I've bolded up here about what we've done with the platform that we'll be launching. We've thought a lot about preservation. So we've built it now on a core trust CL repository that University of California maintains, and that's called Merit. So we can actually think about the persistence of the data publications that are going into Dryad. We're using standards for the discoverability and access of the data, as well as making sure that we can report back on it. So using PIDs for people and the funders and the organizations and that information. Opening up how much data can come in, so not turning away researchers for things that their data set's too big. So Dryad in the past was 20 gigabytes, and when we launch, it'll be 300 gigabytes per DOI and unlimited DOIs to link together. And then thinking, of course, about making the curation public and showing that access with Make Data Count. And for those who don't know what Make Data Count is, there's a great session happening right now, 4 doors down, about that. So bother any of us after. But the big thing that we had to be thinking about is that we have to think about how researchers actually submit their data and how we can support researchers in that way. And researchers don't want to go to datadryad.org and then upload their data. And so what we've done is we are going to be doing these massive API-based integrations. So these names on the left may be completely foreign to you. ScholarOne and Editorial Manager are platforms that about 10,000 journals are on. So Elsevier, Wiley, PLOS, every big publisher uses those platforms. So we went above the publishers, and we have full commitment from the 4 on the left that they are building integrations into the system. So when a researcher submits their article, they can submit to Dryad without ever coming to us. It just happens within the system. AAAS is their own platform. That's why it's the only publisher listed. And then on the right, thinking about all the other things that are happening there. So we have the different kinds of the work environments. I forgot to add Wholetail to this for those that are working in that community, but thinking about how researchers are actually using data, both to analyze and to work with and to contribute. And so we've been working with a bunch of those, as well as the domain repositories, to be thinking about how we can make sure anything going to Dryad should go to Dryad, and we're not anymore taking data that should go to the domains. So something that comes to us that should go to BecoDemo, we should be able to send that over and teach the researcher along the way without just saying no and then not helping them through that process. So I know I'm like rushing through a lot of new things about Dryad, and there's a lot to think about, but we're also thinking about what are other points in this. So Dryad only takes data. We want to support the researchers, especially in the earth and life sciences that have supported Dryad in the past, especially the folks at the UCs and others. And there's code and there's other stuff that we are not equipped for that is just as important. And so yesterday we announced, for those who didn't see, that Dryad and Zenodo are partnering as well. And so this is a step that we're taking to have an alliance between someone that's invested heavily in code, Zenodo, and in code citation and software citation, all that, and Dryad that's focused on curation that Zenodo doesn't do, and we don't do code. So I don't have answers right now on what this is going to look like. It is a statement of intent that the technical director at Zenodo and I will be working together to map what the needs are, how we can integrate our systems, and how researchers can kind of just think a little bit less about 10,000 places to go, and we can make it a lot easier for them to get all their code and their data and their other outputs published and archived and preserved in that backend repository without them thinking about it. And so I've put a link here. This is a staging environment. If you want to see the new Dryad, it is open for anyone to play with. You can talk to me after. We can talk about more. But this is really about how we could put resources in to maintain a place that the researchers really want maintained. And this was our roadmap, and we're excited to see where it'll go next. Thanks.
Any questions for Daniella?
Emilio Mayorga at the University of Washington. I'm not going to ask about ROAR. Inside joke, I guess, 2 days ago. I could ask multiple questions. I mean, a lot of what you're saying, it just resonates a lot at the building of partnerships. I could ask about funding and how this can be sustained when you are focused on, well, it's coming from California, but what you're building is universal. I guess I'm sort of asking, but I will ask another question. And maybe this relates to the idea of collaborations, but also not duplication, but I forget her name. You were talking about having multiple data objects, maybe, but multiple efforts that are parallel. And I'm thinking of Pangea here, that I don't know enough about it in Dryad, but I've always thought of Dryad as being more biological leaning and Pangea being more earth science leaning and also more European. How do you build constructive collaborations with entities that in some way, if you wanted to view it negatively, you could see that you could view them as competitors. The same goes, I guess, with domain repositories. So I know that's big umbrella, but I'd love to hear your thoughts on those connections and productive collaborations with groups that in some way, from a different perspective, or more traditional perspective, could be viewed as competitors for funding, for attention.
Yeah, it's a great question. And to touch on the first point, because I know a lot of people have asked this, while I'm thinking about UC researchers, I'm also mostly thinking about global. Of course, there's a lot of questions about how CDL, UC, and Dryad work together. We have one team. The funding is sustained, of course, through UC for people like me. Dryad is going out with a new membership model for institutions now to find sustainability and not ask for grants anymore. And that is the path forward for that. But that is a great question that you've asked about this, and that's exactly why we partnered with Zenodo yesterday, is that we have to think strategically about this space, and there's only so many people we can compete against, and it's not worth us competing. We should be leveraging each other's features and expertise to actually come together and make this work, especially for us that are involved in the open source world. If we really care about finding the solutions, we have to integrate our systems and just figure out which ones work. Pangea is someone that I've worked with Make Data Count and other stuff, and definitely someone that we're interested in talking to. We really have no intent on trying to compete with the other open projects in this space. There's enough that I can say point blank of commercial problems right now, especially being at UC, as everyone knows about the Elsevier stuff, that we are a little more concerned about and would rather band together with open projects and domains and government to figure out what the right solution is than Dryad being on top. It's really more about what's right for the community.
Thank you for the update on Dryad. It was really good to see the progress you guys have been making on several fronts. One question, you mentioned that you do. I'm Karen Stocks. I'm at UCSD, so we work with you. You mentioned that you do try to refer people to appropriate domain repositories where they exist. Do you have a resource that you use, like RE3, to find those, or is that sort of a list that you guys keep internally?
That is a great question. I'm uninvolved in the curation process as a product person, but the curator, there's 5 full-time curators, and they use all resources like RE3 data and just knowledge of the past 10 years to think about what's right. I know that there are still some cases where data has still gone to Dryad that shouldn't. And so part of the new system is finding ways that we can detect that on submission process, especially by funder. So we've been working with BecoDemo on seeing, okay, the grant will have a specific thing. How many of those are we getting in Dryad that we just should know? We should see it on the first metadata form and shoot it over to them.
Anyone else? I think nothing online.
Just one thing that struck me, this is just a comment, so you don't need to respond, but that this, to me, what you're talking about is really caring about those relationships. And you're working to maintain the good things and trying not to maintain the bad things like the Elseviers. So it's very much in the spirit, I think, of the maintainers. All right, thank you, Daniella. Our next speaker is Jason Gallo, and he will be talking about the scale and value of Earth observation infrastructure.
We shall figure this out. All right, thank you very much. Thanks for the introduction, and thanks to the maintainers for having me here. So I do want to talk about the scale and value of Earth observation infrastructure. And I'm looking at this from an infrastructural lens. I work at Science and Technology Policy Institute, which is a federal research center in Washington, D.C. And we work with executive branch agencies and the White House Office of Science and Technology Policy. So that's sort of looking at it from a interagency macro policy level. So what are we interested in when we want to maintain data? We want to maintain the infrastructures that support the provision of that data. And so what are we really talking about when we say maintaining? What are we maintaining is what I want to get at through this. I'm going to talk about sea ice. Why should sea ice forecasts be maintained? When we talk about care, there's a number of societal benefits that come from Arctic science generally, and these are also true of sea ice forecasting, sea ice analysis as well. So protection of life and property, I mean, that's a very fundamental care issue. These data products are public goods provided for by public investment through government agencies, for the most part, academic institutions, and a large ecosystem. I mean, there are international partners, there are state, local, and tribal partners, there are commercial partners as well. But these goods are not only public goods, but they're merit goods, goods that may not exist without public investment. Economic productivity, they support that as well. Community resilience, another care aspect of this. Fundamental understanding of the Arctic system. So as the Arctic system changes, and there are changes globally, what does that mean? How do we take care of our communities and the infrastructures that exist in the Arctic, but also outside of the Arctic? And finally, they support science and observations to improve decision-making across sectors. So that all of these sectors above, the value from these information products comes from their use as they are applied to decisions. So what's unique about science in the Arctic? I'll just go through this pretty generally. It's remote, but its processes are not isolated. So what happens in the Arctic affects what happens globally. What happens globally affects the Arctic. And the societal benefits are also both local and global. So what happens in the Arctic, again, if we understand sea ice extent and thickness, it benefits those communities, governments, researchers, and commercial interests in the Arctic, as well as international governments, researchers, and commercial interests. A lot of human activity transverses the Arctic. It doesn't stay necessarily only in the Arctic, and as well as activity outside of the Arctic doesn't only affect areas outside of the Arctic. So it's understanding that coupled linkage there. But because the Arctic is remote and sparsely populated relative to other areas in the globe, there are challenges in deploying and maintaining observational systems. And this can lead to gaps in information, which leads to potential gaps in information and data products, which can lead to gaps in the ability for decision makers to have adequate decision to provide for societal benefit. And then many Arctic communities and social and economic infrastructures in the Arctic are vulnerable to these rapid changes. And so what happens outside of the Arctic affects the Arctic and vice versa. So again, understanding what's happening there, understanding how we can provide decision-ready information products to folks both inside and out of the Arctic to maintain that level of care that's necessary is very important. So how do we know what should be maintained? I'll very briefly talk about a study that we conducted over 3 years, an interagency study on Earth observation assessment. So what's the entire portfolio of Earth observations that the federal government relies upon to meet its key objectives? And I can talk about this in great length afterwards, but I'm going to go through this pretty quickly. It was a very large study. 300 federal subject matter experts were divided across 13 teams. Those are 13 societal benefit areas. We talked to then a further 1,000 subject matter experts involved in an elicitation process to understand what information they were relying on and what systems they were relying on to get that information. And we did about 3,000 interviews, so an average of 3 interviews per subject matter expert. What we ended up with is 200 unique key federal objectives. We tried to get federal objectives that don't match one-to-one with an agency mission. So we didn't want to talk to a program manager who said, my job is to measure X, therefore I measure X. How well am I doing? I'm doing very well at my job. We tried to get things that cut across. So looking at things like the protection of life and property is one, especially in the weather area. What we ended up with is 1,700 unique Earth observation products. So in talking to those 1,000 people. We ended up talking to them about the information products they develop. There's about 1,700 from this study. And that traced down to about 1,300 Earth observation inputs. Those are the systems, sensors, networks, databases, and surveys in there. And then we built a model to analyze all of that, and about 54,000 nodes in it. And we're able to then really look at this and how information flows across that network. So this is just to very briefly talk about how we got to this, and I'll skip some of the detail, but could talk about it more afterwards if anybody's interested. We wanted to connect societal benefit at the top, down through thematic sub areas, through key objectives. Those are those 217 cross-cutting objectives I mentioned, down to groups of information products. When we say sea ice forecasts, it's a broad set of products, and this is so people were able to evaluate and weight a broad category rather than individual products. Then we had examples of those products in this tree, and then you have things that flow into that, so intermediate products, so modeled outputs, databases, things like that, and then we trace that down to the individual data inputs. So here's a notional one, which I don't know if anybody can read, but if you run through this, runs all the way from a large societal benefit area at the top down to very specific systems at the bottom, and we trace that information flow. So here's sort of a notional idea of how this data is networked. So that's a tree. You look at it, it's sort of tree-like at the top, but it's a network of roots at the bottom tracing down to individual inputs. But what we're really interested in is this networked part of it. So when we're talking about maintenance, what goes into a sea ice forecast? We talk about that. It's not a single thing. I mean, you may use it as a single information product, or an end user may see one output, but we really want to understand what's happening in the middle, because if we want to understand what to maintain, we have to understand all the things that must be maintained to get to that individual product. So I sort of prefaced this before, but what do we really have to maintain? So this is a composite of Alaska sea ice products. There's 78 observing inputs that run through 11 intermediate products. When we talk about maintenance, what are we maintaining? There are marine observations, those are clustered at the top. There's satellite observations. There are terrestrial, there are airborne, and there are citizen science observations. So we have to maintain some aspect of each of these in order to get to a sea ice forecast. And we don't have to maintain all of them equally, but understanding what goes into a sea ice forecast really opens up the door for understanding what is it that we rely upon. And many of those systems on the left, if you can imagine, we don't fly half of these satellites just to get one Alaska sea ice forecast. They have multiple uses. So when we're maintaining things, the value of what we're maintaining is not just the single end use, it's multiple end uses, multiple products for multiple users at a time. So beginning to put our hands around the value of this opens up the door to a large series of investments, but also that the incredible importance of maintaining this. So if we look in the middle as well, this is something that should be very germane to ESIP. We have a lot of modeled output. That requires a lot of computational power, a lot of investment in cyber, physical, as well as human infrastructures to support that, to produce outputs that can go into a sea ice forecast. So I stole this from WMO. So this is, again, sort of illustrates what are all the infrastructures here that we have to maintain in order to get to an information product. And I thought this was a nice schematic that sort of illustrates that point quite well. So I want to talk about one of the 78 aspects here. It's the SNOTEL system, the snowpack telemetry. So when we want to maintain nodes in this network, there are 876 as of 2 days ago when I checked in this network. This is a station up in Alaska. So in order to maintain that, if it goes down physically, someone has to get up there on snowshoes, maybe 2 people, maybe a snowmobile. That is cost, that is time, that is human effort to get data from that system that is then transmitted into this network. And then in that network, getting that bit of data that goes into a sea ice forecast is one aspect of this entire puzzle. So, these systems measure air temperature, barometric pressure, precipitation, relative humidity, snow depth, water content, soil moisture, soil temperature, solar radiation, wind speed, and directions. That's a lot of information coming from remote infrastructure flowing through a large network as one part of 78 inputs into a larger set of intermediate products that go into one sea ice forecast. So SNOTEL doesn't just support sea ice forecasting. Here's from our study a number of different products. So I don't know how well you're able to read this, but it's everything from Alaska snow cover modeling down through wildlife disease research in the greater Yellowstone ecosystem. So you saw that network is across the United States. So it's a whole network with multiple uses and multiple flows of information that need to be considered when we talk about maintenance. So what? So this is my wrap up in the final minute or so that I have here. When we're considering platforms, a satellite, for example, has multiple sensors on it. When we're talking about maintenance, we can lose one sensor, but it doesn't degrade our ability to produce a certain, so the sea ice product may not be affected by that, but loss of another instrument may do that. We need to be able to attribute specific information, therefore, to specific sensors. And that's when we work through the study that we had to understand those 78 inputs, but which information are we relying on? Or when we talked about SNOTEL, there's about 8 variables that it measures. Which ones are we relying on at any given point in time? And losing a platform may not necessarily diminish the value of any other sensor to any other application. In networks, like SNOTEL, each node is identical, but its location is unique. So what does that mean for information? The value often lies in observations made across the network. So the loss of an individual node may not necessarily impact the network, but aggregate losses may. So it's really easy to defer maintenance when you lose one node that doesn't degrade overall activity, but it's critical. There's a critical threshold. If you keep deferring maintenance, you hit a critical threshold where you have systemic failure. And then data infrastructures. There's that WMO schematic. There is a lot of infrastructure that goes on there. The data has value to decision makers when it's analyzable and interpretable. Information products have value when they're discoverable, accessible, and usable, as Emily had pointed out before, and it relies on a massive data, information, and communications infrastructure. So my final thoughts are: free and open data are not free by any means. The provision of data information products is a result of significant investment. We talked about that a little earlier. And finally, these cyber, physical, and human infrastructures really rely on adequate funding and maintenance. So when we talk about maintaining something, there's an entire set of infrastructures that need to be maintained in order for the one thing that we're considering to actually still have value. So thank you very much.
Questions for Jason? Comments?
Wow. No, really, I think about, products and that there's always inputs, and I thought, sea ice forecasts, you gotta know where the glaciers are and who's calving and what's floating around, but I never thought that level of input products. And when I think about how you want to save all the data that goes into a product, then suddenly you've just made my mind blow up. Because I think how do you begin to do that in a way that 30 years from now you could go back and see if that forecast was right, or could you repeat it, or that type of, and especially when you're going to have to be saving those, you're going to have to rely on other institutions to be saving that data. You can't save all that input for that every forecast.
Yeah, and that's something before we embarked on the study, I also didn't have any idea that a sea ice forecast is really, I knew it was a lot of inputs, but not that many inputs. And how do you fractionalize which bit of which sensor data is going into this stream versus that stream? And then as you mentioned, the archiving it and keeping it of the 10 or so variables that come off of a SNOTEL station, do you need all of them? Maybe, maybe not. And then this is outside of my area of expertise, but is that information then preserved in the final product? So is there an archived version of the sea ice forecast for July 18th, 2019? Certainly there is. Does it then have the ability for the provenance to go all the way back to maybe one station that was important somewhere in Alaska? I don't know, but that definitely opens up some questions that I think when we think about maintenance and think about preservation, long-term preservation and stewardship of these data records, they're well worth considering. And really, I think underscores the massive amount of labor that happens by folks who come to ESIP to make these things possible.
Hey, Jason, Ted Haberman from Metadata Game Changers. Nice to see you again.
Yeah, good to see you.
I'm wondering I was sort of involved in this sort of in the early days a little bit, and one of the things that you didn't mention is sort of the resource of the human resource that exists in the federal government and the academia and other and research or industry as well that supports this stuff. And I'm wondering if you, I mean, I know that you ran into situations where certain observing systems or certain elements in those observing systems depended critically sort of on one person. And I know that, could you comment on that? I know it caused some tension in some situations, and are the agencies thinking about that, or just your thoughts on that?
Yeah, no, that's very much true. I mean, it's not just cyber physical, but also human systems in there, and labor costs get rounded into, depending on the agency, a mission or a program office line or a division, and that's actually quite important. How you structure an agency and how you structure your management, how you want to handle data management is going to come with those additional costs. And you're absolutely right that there are systems, there are data systems as well as collection systems and dissemination systems that are reliant on one, two, or a handful of people that, should they retire or be transferred somewhere else, you may lose a large chunk of the ability to provide that information or keep it or steward it or dispose of it properly even. And I think the answer to how the agencies are considering this would be uneven, depending on the agency and depending on their HR and management structure. They may consider this differently. Some agencies invest very, very heavily in data management, provision of data and dissemination, and others are sort of, I don't want to say just end user agencies, but they're somewhere in between. They gather data from other agencies. So they're reliant in a sense on the labor of another entity in a different budget line and a different part of an appropriation. So sort of an all of government, whole of government question that I think really should be addressed at a high level. And I wish we're being addressed more directly.
Anyone online with a question? No.
Well, it's sort of a follow-up to the previous two questions. So I think that that complex flow diagram you showed that led to WOW, I mean, that was an act of maintenance right there, just creating that thing. And I thought it was interesting. You point out that a node may fail and it's not that big a deal, but at some point there's a critical threshold. Mm-hmm. And so my question is there an entity? Is there a group of people that maintains that flow diagram, that maintains or at least monitors how all those relationships come together and so forth?
That's an interesting question for the break. So I will say that yes and no is the answer, and that there's a subcommittee, the U.S. Group on Earth Observations, that has the responsibility for dealing with interagency Earth observation on the civil side. I'll note Earth observation policy across that. This particular flow diagram and the particular effort that went into that was a government internal report. There are some open questions about the maintenance of that itself.
This is a little in the weeds, but does IARPC play a role?
It is a sister subcommittee, so there is interaction and interplay. We certainly worked when we were working with the community to actually get that flow diagram. We worked with people who participate in IARPC, but are also relevant experts in Arctic research in their agencies. And so yes, there's interplay in IARPC, U.S. Group on Earth Observations, the Ocean Science and Technologies Working Group, the Subcommittee on Global Change Research, all meet quarterly. Basically, the Earth Science subcommittees do meet amongst their relative leadership on a regular basis, and among the 1,000 subject matter experts are folks who participate in all of those different subcommittees. And
sorry, IARPC is the Interagency Arctic Research Policy Council.
Yes.
So it's all the U.S. agencies that are involved in Arctic research, which is actually quite a number of them.
I'm Deborah Smith, by the way, from NASA's Airborne Data Management. This isn't so much a question as a comment. Your statement, free and open data are not free. I want to make a new PR campaign for science and blast that out to the community in our current times to remind the general public that that's exactly the case.
Yeah, thank you all.
So our next speaker is Fred Beach, and he will be talking about the US energy infrastructure. What's past is prologue.
Let's see if I'm smart enough to manage this computer. I always love coming to these kind of conferences and listening to these presentations because they bring back memories, and not always good memories. Just a bit of background. As I was listening to these just most recent discussions and questions, my first introduction to this field really was in a previous life. I was in the United States Navy. One of my last major jobs before I retired from the Navy was I was the Navy's Y2K test coordinator and administrator back in 1988 and 1999. You know, 98, 99. It's been 20 years ago. Remember, how many of you remember Y2K? Talk about a database nightmare, identifying every computer system within the United States Navy and having to test all of them simultaneously at sea and demonstrate to people who had no idea what a computer was that we weren't going to have a problem. And of course, we actually did not have a problem. But that led on to another task immediately following that, because what we learned from Y2K, for those of you who weren't involved in it, was we had another problem called critical infrastructure protection. Go like this if you know what I'm talking about. I got buried in the Pentagon for about a year in critical infrastructure protection, again, maintenance, because Y2K identified we had a lot of stuff in this country that if it broke, the whole thing was coming down. So we spent quite a bit of time from Y2K going into that. And that's kind of, I didn't realize what kind of got me started in this field in my second career in academia was we've got this thing called energy infrastructure that we've been building, maintaining, and unfortunately, in many cases, not maintaining for a long time. And we're getting into the process here over the next 20, 30 years. We're going to have to maintain finally, replace, rebuild, and build new a lot of energy infrastructure in this country, and there is no plan. So if anybody thinks the United States has an energy policy, please come see me in the break and tell me what it is. Because as best as we can tell, there isn't one. Now, again, University of Texas at Austin, the Energy Institute, this study was actually a follow-on study to one we did a couple of years ago called The Full Cost of Electricity. And when you get into these projects, you realize just how much the data is important to what you're trying to do, and finding out if there are even data sets that exist to pull from to identify what we have in this country with regards to energy infrastructure. And energy infrastructure is a pretty broad term. This project is still ongoing. We've got about 24 researchers across campus working on it. It's a multidisciplinary project. And what we're trying to say is, if we really do have several $1 trillion of energy infrastructure that is literally falling apart and needs to be replaced just because it needs to be replaced, not to mention several $1 trillion of energy infrastructure we need to build for the future, and every single one of you has a different idea of what that future is going to be and what we should be building, and is it going to be maintainable, and how are we going to pay for it, and who's going to decide? Well, if you think we have, again, an energy policy in this country, you think somebody is deciding. Well, we do not have an energy policy in this country. I'll tell you right now, I'll break the myth. Who is deciding is every single one of us through our actions in the economy are deciding what is being built and not built, and what our energy infrastructure is going to look like in the future. So the focus of this study was to, one, figure out what we actually do have, what we have in the ground today in energy infrastructure. And I don't just mean power plants. I mean transmission lines, I mean pipelines, oil wells, gas wells, coal mines, rail lines. A lot of our energy or fuels move by rail, shipping lines, transport lines, roads, trucks, everything that moves energy around this country. And then a lot of it pushes it overseas or brings it in from overseas. So we've just about got that cataloged. I'm getting ahead of myself here. This is a 2-hour presentation I condensed to 30 minutes. I'm going to give you in 10. What we've pretty much figured out is, if we look at just the electricity sector, and what we have right now, it's about a $5 trillion replacement cost if we were going to wholesale replace the electricity infrastructure in this country. And just to break down where it is, more than half of it are the power plants. coal power plants, natural gas power plants, nuclear power plants, wind turbines, solar panels. About 9% of the transmission infrastructure. So when you hear all those numbers come out of California and what California is facing right now on just upgrading and maintaining the transmission infrastructure that's burning the state down because it hasn't been maintained for 100 years, that's only 9% cost-wise of the energy infrastructure out there in the utilities. About 35% of it's the distribution network. So when I say it's about a $5 trillion, it's only about $2 trillion in a depreciated cost because a lot of it's very, very old stuff. So as we're replacing it, we're looking at big numbers as we go forward in the future. And should we even be building new transmission infrastructure? Or do you have a vision that we're all just going to have solar panels on our roofs and we don't need transmission infrastructure anymore? You know, should PG&E down in California be starting to rebuild those transmission lines that are burning the state down? Or should they move to a whole new paradigm of infrastructure and perhaps a maintainable infrastructure, a distributed infrastructure, and a very highly networked infrastructure as they go forward? A lot of different answers. But again, this is just looking at the depreciated costs as well as the replacement costs just in the power sector. This is just a meta map of all the power generation systems in the United States, electric power generation. So even down, this doesn't go down to the level of every solar panel on your rooftop, but it goes down to the scale of utility scale solar. The size of the dot is the size of the power plant in capacity, megawatts or gigawatts. The color is just a map of how old it is. So the more red you see there, that is the more depreciated, i.e. the older power plants that have been paid off and paid for and are actually the money makers that your utilities don't want to get rid of. Because once that power plant's made off, it's really making the utilities some money. The bluer dots are the newer stuff. And the thing you'll notice is the older, bigger red dots tend to be to the east and into the northeast. The newer bluer dots are smaller dots and much, much more distributed across the country. As we move to wind and solar, smaller units of generation, more distributed units of generation, and more localized. So kind of where we're trying to go with this, and this is just one more slide. You think the electric power sector is expensive? How about the natural gas infrastructure of this country? $8 trillion. Natural gas pipelines. Some of those pipelines, and as an example in Boston in the city, are made out of wood. I'll say that again, are made out of wood. We have wooden pipelines under the streets in Boston carrying natural gas around that city. And that's why here recently they've had manhole covers basically blowing up into the air as some of those gas leaks from those wooden pipes are leaking. So the scope, the magnitude of this problem we have is just mind-boggling. So the critical questions we're looking at in this study as we go forward, how do we maintain what we have? What should be maintained? What needs to be replaced? As we're going to replace, what do we replace it with? More of the same, or do we move to a new paradigm? And this even reaches down into economics and even academics around the country. We were talking about it early. Alaska, there's a thing up in Alaska called the Trans-Alaska Pipeline. And again, I'll date myself. When I was graduating high school, the question was go to college or go to Alaska and get rich working on the pipeline. Well, I just had my 40th class reunion last year. So that pipeline is 40 years old and it's going dry, it's going empty. There's not enough gas or oil moving through it anymore to keep it viable, which means the state's going to go bankrupt. State of Alaska. Should we maintain it? Well, it's not a maintenance issue. It's should we push anything through it anymore? Do we go up into ANWR and start to tap new oil reserves just to have something to push through that piece of infrastructure to keep the state viable? Or do we let it die a natural death and let what happens to Alaska as a state and an economy happen? So again, this is a very difficult questions, even on individual pieces of infrastructure. Another one, liquid natural gas export terminals. We're building liquid natural gas export terminals in this country to the tune of about $10 billion a year, all in private capital, because we're going to push all this natural gas producing overseas. That's energy infrastructure. And once you build it, you will use it for some period of time. Is that the right direction to be moving? So what really is driving our energy economy and our energy infrastructure is the invisible hand of the economy. There is no government plan except to keep our economy strong, keep our national defense strong, and what you all are voting with are your dollars on what matters to you. And it tends to be the lowest cost energy source or the most convenient energy source. And when I talk about cost, it doesn't have any of the externality costs of your energy decisions tied into that. I'm getting a little bit off track here and I'm probably almost out of time, but the theme of this is we have to pull so much data from existing databases. I told the story last night, when you go to EIA to get all the power plant data that EIA pulls in weekly, monthly, and annually, it comes in FoxPro. Imagine trying to strip all that data out of FoxPro and into something you can use today. I mean, it's great data. It's very detailed and goes back decades. But imagine hiring some poor doctoral student to come up with code that can strip all that data out and put it into a usable format so you can do this kind of work. But one last example, and I'll get off the stage. This is an example of a product that Lawrence Livermore National Labs put out called a Sankey chart. It's our version of it. We're doing another GUI on it to take it onto the web. And just as an example of the decisions we make, if we all decided to drive electric cars, if we all actually did that, all light duty vehicles in the US, we could reduce the energy used in this country by 15% if that electricity came from renewable sources. If, as in this example, all that new electricity demand came from natural gas power plants, which are pretty efficient, it would only reduce our energy use by about 10 quads. Because even a natural gas combined cycle power plant is only about 60% efficient. So having a 90% efficient electric vehicle doesn't really get the benefit you want if you're still throwing a third of the energy away at the power plant in generating that electricity by bringing it from wind, hydro, or solar, or nuclear. So I'll leave it there for questions, because I'm sure I've gone long enough, but it's all about the maintenance. And once you build it, you're going to use it and you're going to maintain it, and it's going to dictate for many years, if not decades, how you live and how you interact with that energy. Thank you. Surely that stimulated at least one question.
I hear a lot about diversification of energy sources. Oh, sorry, Ken Kehoe, University of Oklahoma.
Mm-hmm. My alma mater. I did my undergrad at OU.
Go Sooners, yeah. So my question is, what's the right balance, and is there a way to figure out the right balance of diversification versus choosing a bigger source because you have economies of scale? Is there a way to figure that out as a optimized problem?
I'm biased. We're all biased. I'm a physicist. I'm an engineer. So I always think the most energy efficient approach is usually the most logical approach. Now, that's not necessarily going to be the lowest cost approach. It may not even be the lowest emissions approach, but it tends to be if it's the most energy efficient. It's got to be distributed. It's got to be distributed and diverse, because anytime you're going to, and here primary electricity, and we're electrifying as a country, if you're going to generate electricity, you want to generate it as close to the load as possible. So you're most efficient in getting it from generation to load. That's why, how many of you have solar panels on your roof? Yeah, the only 3 smart people in the room. It goes from that thing on your roof right into the load in your house. I mean, that is the most, today, efficient way to generate electricity, is right on the roof on top of the load where it's going to be used. So I think philosophically, fundamentally, the more distributed, the more diverse the energy generation or the energy power generation, electricity generation, the better. Solar panel on your roof, feeding the electric car in your garage. Now, is that technologically possible today, given our driving habits and whatnot? Not quite, but we're getting pretty darn close. Wind turbines. We spent $8 billion in the state of Texas building transmission lines so we could build the wind turbines out in the panhandle where the wind was the best and bring it into the load centers in the Texas Triangle. That was stupid. It worked great. If we were a country, we'd be number 7 worldwide in wind generation. We should have built it offshore within 10 miles of Galveston, Houston, Corpus Christi. The load centers would have required no transmission lines to bring it inshore. There would have been no losses. The resources better, the load profiles better, everything's better. But we just socialized the $7-8 billion cost of the transmission lines across every consumer in the state. And it all went into the pockets of the wind turbine people who built out where they thought the best site was the lowest cost site, where actually the physics approach, we would have just built it 10 miles offshore. So it gets very convoluted on who's in charge, is there a plan, is there a policy, and what is the desired end state, and what metric are we trying to optimize? And unfortunately, it tends to come down to just cost and near-term cost versus long-term cost. That was a long answer, sorry.
Yeah, Steve Earle from ASU and LTR. Thanks, Dr. Beach. That was just fascinating. You know, it's interesting. I mean, you think about the data, of course, it's just fascinating, but also it's really interesting to me as a citizen, as a taxpayer. I'm wondering, can I access somewhere the 2-hour version? I'd love to hear it.
Actually, I think the best thing for you to go to is go to our website, the Energy Institute, under studies, and look at the last study we completed, the full cost of electricity. And there you can actually go to an interactive tool. I think I had it in here, that produces this map that shows you if you want to build a new power generation source, a new power plant of any type in any county in the United States, what today is the lowest cost option. And what you're seeing on that map is based on a set of criteria we put in it, including externalities like emissions and CO2, and we put a price on carbon. You know, if you were to build today, and actually this map's already a year old on the data, it would either be wind, solar, and natural gas. Those are the 3 lowest cost options depending on where you are. And you can see how it kind of is a resource map. You can see the wind corridor in green. You can see some high solar potential there in the blues and the purples. And then all that red is natural gas, because natural gas is, unfortunately, is just dirt cheap these days. I mean, we're giving it away in Texas and flaring it. It's so cheap, we can't even take it to market. Now, this already is about a 1.5 year old data from when I captured this. You can go to this interactive tool online. You can put in what you think the price of carbon should be, or if there should be any price of carbon. You can put in today what the cost of solar PV is, and it's come down even since a 1.5 years ago when I produced this slide. And if you did it today and put about a $40 a ton price on carbon, that map would be nothing but green. And I think the color for blue or for solar, it'd be nothing but green and blue. 100% green and blue.
Hi, this is Colin Boda, UC Berkeley.
Yeah.
Am I correct that what you're saying is that while we're having a crisis in maintenance coming up, this is simultaneously a huge opportunity?
Exactly.
If you come up with a coordinated infrastructure plan for energy.
Yep.
So that because of the fact that you, as you're pointing out, the cost of rebuilding the same is roughly more or less the same as redesigning the entire system.
Pretty much.
And I have one short unrelated question. Have you considered what rural electrification does with putting batteries in for off-grid solar systems in urban areas as a form of resilience, for example, in California for earthquakes?
Yep. We've looked at that quite a bit in Texas in particular. I mean, being at UT, a lot of the research we do is focused on the state. We've got a couple of small municipal utilities that have very diverse customer bases, where they'll have half of West Austin, very high density meters per square mile. And then they've got this section out towards Fredericksburg where they've got 2 utility meters per square mile as far as customers. And serving those 2 very different diverse areas brings different answers. In one segment, they're trying to get every rancher and farmer who's on their grid to please, 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 please put solar panels on every flat surface on your farm, so I don't have to upgrade all those miles of stuff just to get to 1 meter to serve you. And oh, by the way, if you'll do it, I'll pay it for you to do it because it's so less expensive for me to pay you to do that and become more independent of the grid than me to maintain those miles of wires and lines just to get to that very low customer base. Now, you can use that same analogy even in fairly dense urban infrastructure areas. We're seeing that in New York City in many areas. Instead of upgrading the transformer station to the tune of hundreds of millions of dollars, no, let's put more distributed generation right in that area. We don't need to do the distribution upgrades. So in some ways, economics are moving this that way. In others, they're not. What's the Sunshine State? Florida. What state has the worst solar policy in the country? Florida, because of one entity called Florida Power and Gas, or whatever, FPL, and it's because they hate solar until they figured out, well, if we, the utility, build it, we can build it, we can have you pay for it, and we can own it and operate it. So now they love utility scale solar, but they still don't want you to put them on your rooftop because that defeats their business model. So the Sunshine State isn't, again, from a policy perspective and one integrated utility structure. So it's a battle at every state level, at every city level, at every county level as to what is the answer moving forward. And the answer is different. It is not all just solar, and it's not all just storage, it's not all just wind, and it's not all just unicorns and rainbows. I mean, the answer is different depending on where specifically you are geographically, climatically, and population density wise. And that's, again, part of why we don't have a national energy policy.
All right, thank you, Fred. Alas, we have run out of time, but I encourage you to continue this conversation and come to the Maintainers Conference the 6th to 9th of October. This one insight that I got out of Fred's talk, amongst several, but that I think actually resonates across all of them and really ties in with the theme of the maintainers. Fred said, who is deciding? And he said, it's all of us. And so I think that really rolls into this theme of the maintainers and the advocacy that it's all of us that need to be advocating for maintenance and care. And one thing I wanted to push back against that Fred said is that if we build it, we will use it. Yes, that's true. But then he said, if we build it, we will maintain it. That is not true. And so we have to change that culture. This is really sort of a cultural issue that we have to address. So thank you all, and hope to talk to you more. Oh, and thanks all our speakers as well. Really excellent talks.